morning, everyone. Welcome back. Before we start, let me make an announcement. The homework has been deferred for 3 days, so you can submit your homework 1 anytime on Sunday. But homework 2, the due date will be fixed because the due date will be the beginning time of the take-home exam. And take-home exam takes 2 days, so all these deadlines are fixed.
Could you release the homework to today? So
not today, until Sunday.
but I already submitted, so.
But the other people still need some time. Sorry about that. But many people requested for a deadline this time.
Okay.
Okay, so last time we talked about the proximal gradient. And proximal gradient has the same convergence rate as the normal gradient method. It's 1 over k, and the complexity is 1 over epsilon if you want to find an epsilon solution. This time we are going to see the optimal method. That's the accelerated gradient method. This is by Nesrel. And this method has the convergence rate as 1 over k squared for the convex case. For strongly convex case, in terms of complexity, it's 1 over epsilon square, 1 over square root of epsilon. That's better than 1 over epsilon. And for the strongly convex case, the gradient method has complexity proportional to kappa. The convergence rate is like 1 over the complexity for the gradient method is proportional to kappa, it's big O of kappa, up to a log term, logarithmic term. And for the accelerated method, this is improved to square root of kappa. Remember that kappa is larger than 1, and in many cases it's much larger than 1 because kappa is L over mu. For strongly convex case, L can be much larger than mu. So this is a big number. Square root of kappa is an improvement. And this is indeed the optimal result. And we are going to show the accelerated gradient method for the composite optimization problem, where you do not minimize f, but you minimize some f plus h. This h can be the indicator function of a set, then the problem reduces to minimizing f of x over a closed convex set, or this h can be something that has a simple proximal mapping. And this method solves the same problem as we mentioned before, but last time we used the proximal gradient. This time it's improved result. We make the similar assumptions as before. The function h is closed and convex, and it's simple, has a proximal mapping that is available to us, and f is a closed convex set. We also assume domain of h is contained in domain of f, and also f is assumed to be smooth over some set omega. This omega contains the domain of h. So domain of h is a subset of omega. And we also assume the optimal solution is non-empty. So these are the regularity conditions we need. And now let's see what the algorithm looks like. So we call this method, okay. So here ACG means accelerated composite. C here means composite because we are solving a composite optimization problem. So the way I want to present is not a single algorithm, but a framework. So this general framework contains 3 instances. So this will be a unified proof for, not very unified, but the proof for the 3 methods of this framework will be very similar to each other. And they have a uniform treatment. So here, this is a framework, but it's not a specific algorithm. Here we do not specify how to perform the xk+1, yk+1 updates. Yes.
What's LK?
Yeah, it's something undetermined.
Oh, sorry, I didn't. Sorry.
There will be, so here LK is not determined, xk+1 and yk+1, these 2 updates are all not determined. So we begin with an initial point x0, this is a point in the domain of h, and we light So yk and xk, they are sequences of points, they are vectors, but the little ak, capital AK, and lk, these are scalars. So we also like the y0 to be the same starting point as x, it's x0, and we set a0 to be 0. Then in the for loop, in every step, we need to choose an lk. So this lk, you can basically view it as an estimate of this L. It's an estimate of the smoothness. And with this L, we need to specify some certain condition the L needs to satisfy later on. And after we choose this L, we do this the three computations here. First compute this little ak. Is a complicated computation, but this really has a meaning. I will tell you what the properties of capital A and little a satisfy. And ak plus 1 is just a summation of all the little ak's you had before. And the x tilde k is an auxiliary point, but this is simply the convex combination of yk and xk. And later we will specify the rules. There are three rules to compute xk plus 1 and yk plus 1. And basically that's the algorithm. And we will show the convergence on the yk sequence, not about the x, but the y. So there are three rules contained in this framework. The first one is called FISTA. FISTA comes from this name comes from a paper. It's a well-known paper in image processing and optimization. And because the algorithm there is named FISTA, so this rule inherits this name. So here we compute the. So before we jump into the rules, let me first give you some definitions about the L. L needs to satisfy some definition. Okay, so we first define the solution to this subproblem as y of x to the k lk. So given a pair x to the k and lk, we can solve this by just one proximal mapping of h. This is like the subproblem we need to solve in proximal gradient method. remember that we first linearize f at a certain point and keep h as is and add a quadratic. And this can be written as the prox mapping of h of x to the k minus the gradient 1 over lk, lk inverse times the gradient. These two are equivalent. So this y is basically just this proximal mapping. Given x to the k and yk, lk, I can find a solution to this, and I call this just as y of something. This is a solution. And we say lk is a good local estimate of L if this condition is true. This is a curvature. This C of something is a curvature less than or equal to L. And C is defined in this way. You can show that if Lk is equal to L or greater than or equal to L, then this inequality is always true. You see over here? So this is just the function minus its linearization. View from the Taylor's expansion, this will be some second order information. And divided by this norm square, you get the curvature, a local curvature at this point. Right, so the left-hand side is just computing the local curvature at this point for the function f. And we know the global curvature for f should be L. The global estimate for this one should be L. Because you can show this is upper bounded by L for any pair y and x tilde due to the smoothness. There is a smoothness inequality we had mentioned before. So this inequality should hold for any Lk greater than or equal to L. But if you use a large L, that will slow down the convergence rate. So we want to find a small L, but still maintain this key inequality. That's the goal of this inequality. If you use the conservative estimate L, this is always true, but we do not want to use that. We want to use some small information, the local information. So that's the goal here. We want to use some local estimate of L. And suppose your L is good enough, it's a good estimate for the local curvature of L, then we can do the following computation.
What if L itself is already really small? Can I choose L as Lk?
If your L is small?
It's already small.
Yeah, if it's small, it's okay. Or if so the way we do this, the reason why we do this, one reason is we want to make the convergence rate faster. Another reason is because sometimes you do not know L, right? No matter large or small, you don't know it. You just need to do some estimate. So anyway, you need to estimate it. And this would be a good criterion when the estimate should terminate. Any other questions about the definition there?
If we use L, we reduce to the proximal gradient method.
If you only do this step, that's proximal gradient, but we are going to put this step here. So with step 1, this is an additional step compared with gradient, proximal gradient. So with step 1, you can improve the complexity and convergence rate. You can make it you can make it faster by doing step 1. And also, we have two iterates, xk and yk, and another auxiliary iterate, x tilde k. So in this algorithm, you have three iterates, x tilde, x, and y. But in the original method, we only have the x iterate. That's another main difference. You maintain three sequences.
Now I have a question. What is the x tilde k used for?
X tilde k is used here.
To calculate the
To calculate the,
LK.
not LK, to just compute this one, this y. You need this x tilde k. That's why I didn't use other notation, just x tilde k. This is exactly the x tilde k computed in step 1.
Y is what? The Y there is YK.
Yeah, I'm going to tell you what this y is used for. It's used for the yk sequence, the yk plus 1.
Then how do we choose LK?
LK is something satisfies this.
So that's both used for choosing Y and LK.
Yeah, that's right. So this one here, I will make the algorithm clear. It will be a loop. There is a loop here, internal loop to choose the LK. Because here, if you guess a random L, right? If you guess a random L, you can not guarantee whether this is true or not, right? Even though you make this part large, you make the LK very large, but this one is, you still don't know it, right? Before you do the computation, you don't know. And you need to try one L. If it fails, you need to change the L, try it again. But with a fixed number, no, with a finite number of iterations, this inner loop will terminate.
It will decrease. It will.
We want the L to increase. You begin from a small L until some large L. So in the end, if this L is close to this capital L, just L without K, it should be fine, right?
Yeah.
We use F here to denote this is the Fisher rule. So YK plus 1 in the Fisher rule is exactly the one we have seen. So the YK plus 1 is exactly the Y we mentioned there, and the X first you have this YK plus 1, and you also have the XK from the previous iteration. We first do an extrapolation, right? Noting that this constant together with this constant, this minus this is equal to 1 because of the definition of AK plus 1, right? This minus this is just 1. Right? So this is an extrapolation between the 2 points. And then we do a projection onto the set omega. Remember, the f is differentiable over omega. So we need to project back onto omega, and then, because this point is actually in the domain of H, since you are minimizing using this subproblem here, so the solution is in the domain of H, otherwise it's not finite, right? So this is in domain of H, this is in omega, so here we have a chain. It's in domain of H, and it's contained in omega. So both points are in omega, and hence the Holmes combination X tilde is also in omega by convexity. We assume, furthermore, we assume the set omega is convex. So that this point is in omega, and hence that's why we can always take the gradient at x tilde k. This is just to verify the point is differentiable. The function is differentiable at this point. And the second rule is called AT rule.
Can you say again why it's equal to 1? Minus
AK plus 1 minus AK is little ak.
Yeah.
And divided by little ak is 1.
Okay. Thank you.
The second rule is called AT. This is by a paper by two people with initials A and T. And we use little a to denote this is by the AT rule. The second rule is computing. So it's computing differently. Here, y is the solution of some optimization problem. Here, y is just a combination of 2 points, the yk and xk plus 1 by this rule. And xk plus 1 previously is this extrapolation and projection, but here it's a solution to this optimization problem.
Sorry, what's U in this?
It's x, sorry. I sometimes use x and u interchangeably for the argument in the optimization problem. Third rule is called LLM. This is not a large language model. This is by the initial 3 optimizers. This is Lü, Lan, and Montero. And here we use the yk plus 1 update from the Fisher rule and the xk plus 1 update from the AT rule. So this takes just part of each rules before. And here we saw one proxy mapping for H in the Y step. But the X step is usually simpler than the proxy mapping. This is a projection onto a set. This is simpler than proxy mapping. And here, the YK plus 1 is easy, just a convex combination. But XK plus 1 is more complicated because this involves proxy mapping onto H. Right, so here we just have one proxy mapping, but this method has 2 proxy mappings. The yk plus 1 is from here, has a proxy mapping, and this x also has a proxy mapping. So this method is more computationally expensive than the other 2. Okay, so here we define, in this lemma, we define two linearizations. So this is gamma tilde k is a linearization of f plus h. If there's no h or h is an indicator function, this is just a linearization, but we keep h as is. And the gamma k function is really a linearization. Sorry, this is again x. It's a linear function in a fine function in x. And we have the following statements. First, the gamma k is always underneath gamma tilde k, but they agree at the same point. They agree at the point yk plus 1 f, the yk plus 1 from the Fista rule. And moreover, these two minimization, the x is in Rn. These two minimization, here we only change this. One of them is gamma tilde. If you change this gamma tilde to be gamma, they still have the same minimizer as yk plus 1 f, and they also have the same function value. And gamma tilde k is also underneath function phi f plus h, and the xk plus 1 from the Fista rule, the projection to omega, is actually a minimization over the set omega. Any question about the Simon?
What is phi x?
Phi is f plus h we wrote here before.
Okay.
We are minimizing phi is f plus h. Okay, so B is easy to verify. Gamma is a linearization of f plus h. So linearization of f is underneath f because of convexity. And this is obviously underneath f plus h, which is phi. Okay, and this one is also easy to verify by using the definition of gamma k. So this is a linear function or a fine function, right? So with this quadratic, this is just another quadratic function. So you can solve the solution. This has a closed form solution, right? This closed form solution is the extrapolation in the projection there. So after the projection, you find a solution over the set omega. So this is also easy to verify. This equality is also easy to verify. Just plug in the function value, the point yk plus 1f. This linearization, this inner product goes away, it's 0. So what's left is this one, right? So gamma k plus 1, gamma k at this point is the same as gamma tilde k at the same point. And this part, so you need to show this statement and this statement together. Because this is again, for example, this part is easy to verify. This is again a quadratic function. You can solve the solution, find the exact solution. This is equal to yk plus 1 f. Because yk plus 1 is given here, so if you solve the solution, you will find yk plus 1 f is exactly the minimizer for this one. And for this part, this is by definition, right? Yk plus 1 is y of x to the k, lk, that is argmin of something. So this is also verified. The last thing to show is yk is underneath gamma k is underneath gamma tilde k. Basically, this is actually so we are using the convexity again. First of all, we need to note this is a convex function because this is a linearization and this is convex. So the sum of the two is still a convex function. For a convex function, gamma tilde k, you can show that gamma tilde k x is greater than or equal to so here we do a linearization. This is a linearization of this function at this point evaluated at x, right? This is the function value at this point, and this is the inner product term at that point, right? And here G is a subgradient in this subdifferential. So comparing this part with, so we want to show this gamma tilde k is above gamma k, and our goal is to show the linearization is exactly gamma k. So you just, these two terms are the same. So here you just need to verify this G has the form Lk times this difference. And to verify this, we need to use the optimality condition of this subproblem, of this problem. With that, you can find the subgradient has to take this form. So that gives you why gamma k is underneath gamma tilde k, just because of convexity. This is a convex function. Okay, so I'm going to skip this proof. This is basically we're just using convexity and optimality conditions. All these statements are easy to verify. This is a statement about the sequence x and y, and here it's about the sequence, the scalar sequences, scalar sequences ak and little ak and capital AK. So these two statements holds for nak greater than or equal to 0. Let's prove the first one. Remember that capital AK plus 1 is equal to AK plus little ak. And we want to show this is equal to LK AK squared. Noting that in terms of little ak, this is actually a quadratic function, right? So you can rewrite it as and if we want to find a solution between little ak and capital AK, we can solve this quadratic function, right? So the AK is 2LK. One of the solution gives us this. Right? And this is exactly the definition for little ak. So you can go all the way back to show this is true. From ak is this the solution to this function, and do a reformulation, you can show statement A holds. here we again, to show statement B, we start from AK plus 1. We can use the definition, it's capital AK plus little ak. And here's by definition of little ak. Just plug in here. And here we throw this plus 1 inside the square root array. We get this term. And then we can show that, easily show that this is written out to this square term. Right. And hence, with this, we can show that. So we have, if you take the square root of this inequality on both sides, then you have AK plus 1 right. So if you sum them up, then in the end you can show capital AK written down to A0 plus and this is 0, right? Because definition A0 is 0, so it goes away. And then you take the square of the inequality, we recover this statement. Okay, I'm going to erase this part. This general proposition holds for the whole framework. So it holds for every single rule there. So for every k greater than or equal to 0, and for any x in domain of H, we have this quantity. Let's now go to this quantity. So this one can actually be, for example, let's call it some eta k of x. This is a Lyapunov function. Right? This is a Lyapunov function that is decreasing. Right? This is actually eta k plus 1. And this is true for every rule there. So, but we need to prove them one by one, but the proof will be very similar. So let's first see the FISA rule.
So it's decreasing in k.
Yes, yeah. It's a sequence of, so view this as a, for any fixed x, this is just a value, a scalar. It's decreasing sequence. That's why it's like a Lyapunov function. the yk and the xk here, they mean the ykf and xkf because it's here we are always talking about the Fizer rule. So here I skipped the superscript f, but it should be clear all the y and f, all the y and x mean the one from Fizer rule. The first inequality, so here you can ignore this ak, gamma k, yk. These two are the same. Just check what's left here. Here, this is because xk plus 1 is the, by this lemma here, by this statement, xk plus 1 f, the x here is xk plus 1 is xk plus 1 f. xk plus 1 f is the minimizer for this subproblem, right? And this is just the result that we used again and again. So if you have this minimizer, then for any x, this function value is greater than or equal to this function value at the point of the minimizer plus another quadratic, right? And that quadratic has the same parameter as the strong convexity of this function. This function is just convex. This one is one strongly convex. So you can add another quadratic. But we put this quadratic from the right to the left, so we change the sign here. This is the other quadratic we should add here, right? This is a function value for any x. It's greater than to the function value at the minimizer, but you have some room to put another quadratic function. That's this one. Right, this is property we used several times. And after that, so here we combine the two functions together into this one. This is by convexity. The function gamma k is convex. It's just an affine function, so it's convex. By convexity, a gamma of y plus little a gamma of x would be greater than or equal to right. This is by convexity. And the y is yk, x is xk plus 1. And here, this is a Combs combination that we define by, we denote by y hat k plus 1. Right, so we have the first part. The second part is just a reformulation using the fact that both yk plus 1 hat and x tilde k, they take the form of Combs combination. So this is just by reformulation using the definition of these 2 points. Okay. This is just some simple calculation. And the last part here, we just factor out this ak plus 1. Right? If you factor out, you have this gamma k. And if you factor out, what's left here is ak plus 1 over little k squared. Remember, we showed that ak plus 1 is lk times little k squared. So what's left here is just lk. Okay. So we continue from this part, the right-hand side of this. It's always hat. Oh, sorry, this line is here. So if you start from here, the right-hand side over there, just ignore the ak plus 1. This is greater than or equal to the same function, but at the point yk plus 1. We change all the y hat to the y. This is because we just, the lemma we wrote here, we show that yk plus 1 is a minimizer to this problem. Right, so this has a smaller function value compared with this one. And from here, we use the fact that gamma k and gamma tilde k, they agree at the point yk plus 1. So this is an equality. And from here to here, we use the fact that Lk is a good curvature, it's a good local estimate for the L. So that recall the good curvature means that the C of yk plus 1 xk tilde less than or equal to Lk. And this means f of yk plus 1 minus linearization of yk plus 1 right, this is what the good curvature, good local estimate of L means. It just means this inequality is true. If you rearrange the term, put this to the right, divide everything by 2, you have this term, and move this to the right, it's linearization plus a quadratic, we're down to f, right? And here the difference is just this gamma tilde is linearization plus h. The h part cancel with each other. Right? So this is basically the linearization plus quadratic, greater than or equal to the function f. So that's what exactly this inequality is saying. That's the this inequality is where we need this condition, and that's why this condition is defined in this way. It's just a reformulation of this inequality. We just want the linearization plus quadratic greater than or equal to the function phi, because it holds for the true value L. We just want this local estimate to inherit this good property as a smooth function, but we want something local. This can be small. So now we have the right-hand side is lower bounded by phi. The first inequality here is just to rewrite this inequality, right? We put this one to the left and move the quadratic terms here. What's left here is gamma k, right? Because gamma k is underneath gamma tilde, so both functions are underneath the counterparts with gamma tilde k. And also note that we also show that gamma tilde k is underneath phi. This is just linearization plus h, so it's underneath phi because of convexity. So we can further upper bound it with phi. And here we are using the fact that ak plus 1 is capital AK plus little ak. So we just rewrite it in this way. And now you can combine the terms. Put all the ones with k on one side, put all the ones with k plus 1 on the other side, then you can show this claim. Right, so then we show with Fister rule, we really have a decreasing sequence. The gamma k for any fixed x is decreasing. Now let's do the AT rule. So why the same inequality holds for the AT. Okay, we are done. So the proof is quite similar. Let's see. This should be correct. So for AT rule, the argument changed with gamma tilde k. So we use gamma tilde k instead of gamma k. The reason is because the xk plus 1 for AT is this minimizer, and this is, by definition, here is gamma tilde, right? This is gamma tilde. So we again use the strong convexity of that function. Here you have no strong convexity. Here is one strongly convex. So we again use the same property that you can add a quadratic here, but this is gamma tilde, right? And these two are the same. So we still have the first line here. Note that this xk plus 1 is xk plus 1a is from the AT rule. And the second line here is by the fact that, so here we again, there are two steps. You first show this with gamma tilde k. So we again use the, here we again use the convex combination for the 2 points, right? We do convex combination of these two functions. So it's greater than or equal to ak plus 1 gamma tilde k of the convex combination point. And here the convex combination point is exactly the yk plus 1 in the AT rule. This is like the yk plus 1 hat we had before. Right, so we have this line. And because gamma tilde k at this point, no, here we, so let's add one more line. Plus the same quadratic as here. This is because gamma tilde k is above gamma k for any point. So we have this inequality and we copy the same quadratic here. And from here to this line, we just do a reformulation, right? Because this y is actually like the y hat before. This is y hat, yk plus 1a there. It's a common combination. X tilde k is also a common combination. So this is Oh, no, sorry. Here we don't need to use the fact it's complex combination. Here it's just because we factor out ak plus 1 and ak plus 1 over little ak squared is just lk. Here we don't need to use complex combination property. And from this line to here, it's similar to what we did here because oh, sorry, we don't need to do this step. This is correct. We just change this to gamma tilde. That should be fine. So sorry. From here to here, we just use the fact ak plus 1 over little ak squared is lk. And from here to here, we do the same argument as before because lk is a good local estimate for L. So the linearization plus quadratic is over function f. And here we have the same h part. H part cancel with each other. So this is true. Right here, we never use gamma k. We just use gamma tilde k.
So basically, we change every gamma k to gamma tilde k.
Yes, here we change gamma to gamma tilde. But in this argument for the Fista rule, you have to work with both gamma and gamma tilde. But here we just work with gamma tilde. There's no gamma.
But how about afterwards?
From here, afterwards, you just do the same argument as here.
Oh, okay.
But this is, let me see. Yeah, you directly go from this line to this line, right? There's no gamma. Direct go from here because here is gamma tilde. Right. This step is only for Fista, but not for AT. Right, this is for Fista only. Now let's do the LLM. Okay, so for the LLM rule, the XK update is the same as the one in the AT rule. So the first inequality still holds, right? Because they are both by the same argmin. The first line still holds, and for the second line, we again use convex combination. But this convex combination point is not in the LM rule because the convex combination is a y point from the AT rule, but this yk plus 1 is from the Fista rule. So we again introduce the notation yk plus 1 hat. This is a convex combination point. This is also the convex combination point. And for this step, we do nothing but use the property for capital A and little a. So we have this LK again. And from this part to this part, we use the fact that yk plus 1, the one really comes from the Fista rule, right? This is our yk plus 1 is from the Fista rule. For the yk plus 1 from Fista 1, we show it's a minimizer of this function, gamma tilde k plus a quadratic. So this is smaller than or equal to this function at the yk plus 1 hat point. And from here to here, we use the same property that Lk is a good local estimate for L. So this is true, and you can follow this analysis again. And this step is skipped. It's only for phi step. So now we show LLM also satisfy this condition. Okay. Previously, we just say we want LK to be a local estimate for L, but we didn't specify how to choose it. The naive way is if you know L, then you can take LK to be always just as L. And then with the lemma for the lower bound on AK, we have a summation over 1 over square root of LK and take the square. For that one, replace just every LK by the L. Then you find a lower bound for AK like this one. And you can also do an adaptive search for LK. Remember that we need the C y of x to the k LK x to the k to be less than or equal to L. Okay. This is a criterion for LK. So in every step, for every fixed k, you propose an LK. You propose some LK. And then you do this test. If it fails means this is larger than L. Then it means your L is small. Probably you want to enlarge your L. Then you can multiply the L by 2, for example. Just scale by some factor larger than 1. Probably multiply by 2. And then now you try this LK again in this test. If it's true, then you return the LK with this LK. Otherwise, you go back to this change. You just multiply it by 2, double it, and try it again. So this is an internal loop. But this internal loop will end in a finite number of iterations, because in the end, the L can be no larger than 2L. Because suppose this is your previous test L is something like 0.9L, but this your LK is 0.9L. But this still fails because this is smaller than L, right? But next time your LK is going to be 1.8L, but this is because this is larger than L, so the test must pass, and then you should return this 1.8L, but it can never go beyond 2L, right? If it's 2L larger than 2L, then it means last time you are already larger than L, so you should terminate last time. So this is no more than 2L. So with this bound, replace this bound to the lower bound on AK, then you can find this bound on AK. It's k squared over 8L. So anyway, the AK is at least on the order of k squared over L. And so the final statement is the final convergence is for any k approaching up to 0, AK 5yk minus phi star equal to 4L. So the proof is very simple. We just combine these two results together. From here, you can see this can go all the way back to eta 0. Right? So AK by YK. Now we take this X to be X star, to be the minimizer. Right, and then you do a reformulation, phi of YK minus phi star. Because A0 is 0, so phi y0 minus phi star goes away. What's left is just the distance term. And divide everything by AK, you get this upper bound on the function value gap. And because AK is on this order, so plug in this value. This is the lower bound, right? Plug in this value on AK, you can show this upper bound on the function value gap. So this really gives us an improvement on the convergence rate. Previously, we just have 1 over k, but now we have 1 over k squared, right? And in terms of an epsilon solution, if you want to make this smaller than epsilon, then the k is on the order 1 over square root of epsilon. This is the improvement that we are looking for, so that now the algorithm is optimal. There's a matching lower bound, saying that for any algorithm for solving this kind of composite optimization, this is the fastest rate complexity, smallest complexity that you can achieve. So that this is optimal. The upper bound matches the lower.
So just to make sure, so that lower bound is for first order oracles, right?
Yes, for first order oracles. For second order oracle, we can improve it.
And I just have one question about L as well, or LK. So that's kind of premised on you choosing an LK small enough. So suppose, I imagine it's generally not the case, but L happens to be very, very small for your function. Is there a way of knowing that you chose an LK smaller than it? Other than just going to the range of like floating point error?
You mean the final LK?
Well, no, the initial LK. So you have to start with an LK smaller than.
Yes, yeah. There's no theoretical guarantee either. Initially, you just begin with some small L.
Okay.
Maybe you can take some random points to do a very rough estimate on L.
Okay.
Right? Because this L is for every pair x and y, but you can take maybe 1,000 pairs to get a taste how large this L in general is. But you choose a very, very small L, begin from that.